The ideal gas equation, which is also called the ideal gas law, is a mathematical relationship between the four measurable variables of a gas: the pressure, volume, number of moles, and temperature. In this video, I am going to show you the ideal gas equation, and we're going to practice using it to solve this problem down here. Before we get into that, though, let's talk a little bit about this concept of an ideal gas. What exactly is an ideal gas? First thing you need to know about an ideal gas is that it is not real. There is no such thing as an ideal gas. When a chemist refers to a gas as being ideal, this just simply means that we are applying a set of assumptions about the behavior of the gas. And we use these assumptions to make it easier for us to mathematically model the properties of a gas. These assumptions that we're making about a gas is, first of all, that it has no forces of attraction or repulsion. A real gas is attracted to other gas molecules or to the inside of its container, or it is repulsed by other gas molecules or the inside of its container. Either way, a real gas exhibits some forces of either attraction or repulsion or both. And these forces of attraction or repulsion cause or have an impact on the motion of the gas molecules. Maybe they help to pull the gas molecules together, or maybe they help to direct the gas molecules to move apart from each other. Either way, these real forces of attraction or repulsion in a real gas has an effect on the motion of the gas. An ideal gas, because we're modeling that it has no attractive or repulsive forces, has truly random motion. The second assumption that we make when we describe a gas as being ideal is that it has perfect collisions. This is something that we talk about in physics. A perfect collision is one where when two objects collide with each other, the force of that collision does not result in the loss of energy through sound or friction or heat or anything like that. So when we say that a gas is an ideal gas, that means that we are assuming when two gas molecules collide, or when a gas molecule collides with its container, there's no sound associated with that collision, there's no friction or heat lost due to that collision. It's a perfect collision. And this is a reasonable assumption for us to make because the gas molecules are very tiny. When they do collide with each other, there isn't much energy that is lost during that collision. The last assumption that we make about an ideal gas is that the molecules in the gas have no volume. Don't get this confused. We are not saying or assuming that gases have no volume. We are saying that the molecules themselves inside a sample of gas have no volume. So if we had a balloon and we wanted to describe the volume of the gas inside the balloon, we would just use the volume of the whole entire container. We would say this is the volume of the gas. We would not take into consideration that inside this balloon we have several molecules of gas, and each one of those molecules has its own volume. We would not take the individual gas molecules' volume into consideration. So these assumptions are really reasonable for an average chemist to make because all of these different characteristics have pretty small, pretty minor impacts on the variables: pressure, volume, number of moles, and temperature. So for a typical scientist, it's perfectly okay for us to make these assumptions, and it's not going to have an impact on any calculations that we might do. Let's take a look at the ideal gas equation itself. It says that the pressure of a gas times the volume of a gas is equal to the number of moles of the gas times a constant R times the temperature of the gas. These variables, when we plug them into the ideal gas law, it's very important that we use the correct units for all of them. P, as you know, is referencing the pressure of the gas, and that has to be expressed in units of atmosphere. V, as you know, is the volume of the gas. That needs to be in units of liters. N, of course, is the moles of the gas, which has to be in units of moles. And T, the temperature, has to be in units of Kelvin. And this is the one that students most commonly mess up. The most common unit error in this equation is to put temperature into this equation in units of Celsius. R, which we refer to as the ideal gas constant, is just simply a constant that makes this mathematical relationship work. It is an experimentally determined number, and its value is 0.08206. The units of R are kind of weird. They are liters times atmospheres over moles times Kelvin. And the units are just such that they work with the units of all of the other variables in the problem. The ideal gas constant, R, is one that you use often in these types of problems, so it's one that you want to commit to memory, aka memorize. So let's take a look at this problem right here and see how we can use PV equals nRT to solve this problem. This problem is asking us to determine the volume of 1 mole of an ideal gas at STP. So first of all, let's talk about that, STP. STP stands for standard temperature and pressure, which I've talked about a little bit before. Standard pressure is 1 atmosphere, and standard temperature is 0 degrees Celsius, which in Kelvin is 273.15. STP is a really common phrase used in problems involving ideal gas calculations. So this is something that you'll see quite a bit and something that you want to keep in mind. This problem, let's take a look at it again, is asking us to calculate the volume of a mole of an ideal gas. It doesn't even tell us what it is. It could be helium, it could be neon, it could be nitrogen, it could be oxygen. It doesn't matter what it is. Any gas, doesn't matter what its identity is, any gas we could assume any one of them for this equation. We're being asked to solve for the volume. We know that the number of moles is 1.00, and then our pressure and temperature variable over here. So we want to take our ideal gas equation, PV equals nRT, and we want to start by dividing both sides by P, which allows us to isolate that volume variable. So we get volume equals nRT over P, and in this form, it's ready for us to just plug all of these numbers right in. Volume equals the number of moles times the constant R times the temperature divided by the pressure. And the problem tells us that we have 1 mole. It tells our ideal gas constant, we're going to plug that in, 0.08206 liters atmospheres over mole Kelvin. The temperature, 0 degrees Celsius, 273.15 K, and we're going to divide that by the standard pressure, which is 1 atmosphere. And when we work all of this out, we get 22.4 liters. Let's actually take a look at how the units cancel in this equation. Moles cancel each other out, Kelvin cancels out, atmospheres cancel out, and we're left with liters. So there's a particular reason why I wrote this such a large number. This is actually a really important number in gas problems. This number, 22.4, we refer to as the molar volume of a gas, of an ideal gas. Molar volume of an ideal gas. This is, like I said with this problem, we weren't talking about any particular gas, neon, helium, hydrogen, it could be anything. No matter what the gas is, if it is an ideal gas for any ideal gas, if it is at STP, standard temperature and pressure, 1 mole of that gas has a volume of 22.4 liters, which is what we just proved with this equation right here, plugging in 1 mole and the conditions of STP. So this concept for any ideal gas, 1 mole is 22.4 liters. We're going to use this relationship to help us make some quick conversions between moles and liters in future problems. So this is something that you want to keep handy.